Okay, it seems everything is fixed now. Apologies again for the technical issues that we've been having here on site, and of course to everyone connecting online. And yeah, welcome to KiboCUBE Academy Live. We're here on site from Tunisia in Tunis. We're very excited to be here. And of course, we're connected to everyone around the world through Zoom. So KiboCUBE Academy, it's actually a project we started during the pandemic. So this is the first time we're doing it on site. So we're very excited. Whoops. Okay, hold on. Okay, fantastic. So before we begin, the Wi-Fi code, I think almost most of you have already connection, but it's the main Science City one. So if you want to connect to Wi-Fi, please use that one. If you have, for the on-site people, if you have any questions, we will have it at the end. So please raise your hand and we will have someone with the microphone running around for you. And please answer our questionnaire before you leave. The code is here. I hope all of you can read it. I'm going to keep this up. For the people online, please use the, I wrote chat box, sorry, it's actually the Q&A part. So please use the Q&A function to ask us any questions. We will be having a Q&A time, and we will be having 2 Q&A times. So please make sure to send them in by them. And of course, please answer our questionnaire that we will be putting in, not the chat box, but a different function. My colleague Wenbin from UNOOSA will be putting up the link, so please make sure to answer our question before you leave. And to everyone, please use the hashtag Access to Space for All, KiboCUBE, KiboCUBE Academy, to help us promote this event. We're active on Twitter, Facebook, LinkedIn, Instagram, and basically everything you see there. So today's agenda looks like this. We will begin with the opening remarks, going to the keynote. After that, we'll be giving you an overview of KiboCUBE, and then talking about the different deployment services of CubeSats from the ISS. And after that, we will be connecting with Japan, with the professors from Japan to talk about CubeSat technologies and CubeSat launch and operation. And we will be having Q&A as well. So with this, I'd like to bring to the floor my colleague, the Chief of the Space Applications Section of the United Nations Office for Aerospace Affairs, Mr. Luc St-Pierre, for the opening remarks.
Thank you, Hazuki. And you saw it said 3 minutes there. Forget it, I never talk. Only 3 minutes. D'abord, souhaiter la bienvenue. Puis aussi noter, j'étais ici en Tunisie, c'était mon dernier voyage en fait avant celui-ci. Littéralement, je suis parti le jour avant le premier confinement. Donc, j'ai l'impression de fermer un cercle un peu aujourd'hui. J'espère franchement que vous tous et si vos familles sont en bonne santé. So I am Luc St-Pierre, Chief of the Space Applications Section of the UN Office for Outer Space Affairs. We're based in Vienna. We're a small office, probably one of the smallest offices of the UN Secretariat. But as you know, with space, we have the largest territory, so we're very active. The KiboCUBE Academy for us was a new model when we started to talk about it with JAXA a couple of years ago and UNISEC. But that completed what we were trying to do at that time, to provide more and more information as possible in relation, not only to KiboCUBE, but to the science and the technology of small satellite. We were able, and this is not a minor feat, we were able to integrate in an amendment to integrate this collaboration with the Academy into our cooperation agreement with JAXA. So that formalized it for us, and it's very important. This amendment with the aim was to find ways to promote capacity building in small satellite. Of course, in support of the KiboCUBE project that you will hear about today and tomorrow. But also we see now in much broader range of activities related to space science. There's a huge potential from the network, and we hope to benefit from it. Since this agreement was signed or modified 2 years ago now, we have delivered about, I think, 7 webinars directly under the label of this collaboration. And we've pre-recorded with UNISEC and JAXA about 20 videos. So there's already a wealth of resources, and that's all available on our website. And those deal about small satellite engineering, but also about different subjects. Let me check. Should have brought my glasses, but about safety, about management, about communication, power control. There's a range of sectors. So from the beginning of your development in small satellite engineering, we're going to develop more and more material. As Hazuki said, first live event, one of the first live event of our office in 2 years. We see that as a starting point also to work with the academy. As I said, we want to work not only on the KiboCUBE project for launching small satellite with JAXA, but on space science in general. And we hope we can develop other collaboration in the future. And for that, we need ideas, suggestions. And this is a little bit the idea of this event today. So thank you very much. And I'll leave you back to Hazuki. Thank you.
Thank you very much, Luc, for opening the floor for us. And now I'd like to invite to the floor Mr. George Maeda. He will be giving us a keynote.
Thank you, Hazuki, for the introduction. I want to thank JAXA and UNOOSA for this opportunity to speak to you this afternoon here in Tunisia. With my work at the 2 universities, I've been to Africa many, many times, but this is my first time in Tunisia. So it's a great pleasure to be able to stand here and speak to this Tunisian audience today. My name is George Maeda. I was assistant professor at QTech from 2015 to April this year. I recently retired, but I have a lot of experience with Africa. Before QTech, I was at QDI for 10 years. That also took me to Africa many, many times. So today the title is Building a CubeSat a Good Way for a Country to Get Started in Space? It's framed as a question, but I believe the answer is yes, and that's what I'll talk about today. Okay, so a primary goal of KiboCUBE is to help countries get started in space by inserting into Earth orbit one new CubeSat for such countries. But that begs the question, why do countries need to get started in space? So let's take a quick look at African countries that have placed satellites into space. Don't scrutinize this too much because this data is 2 years old, but it gives you a rough idea of where Africa is. So as of June 2020, 11 countries in Africa have launched a total of 38 satellites. These were often purchased from abroad, but I want to say this: if you buy a satellite, you acquire nearly zero design and manufacturing skills. You don't really, it's like buying a smartphone, you really don't learn much. So these are all the countries in Africa, and the red ones indicate that a nation has put a satellite into space. Summarizing, there's about 58 countries in Africa, 11 have done satellites. That means 47 have not done it yet. Mauritius was a winner of KiboCUBE, the third winner. And please download my presentation file. You can get it from the UN website. And then click on this link and you'll get a 50-page document created by Mauritius about their experience of building the first satellite and then having KiboCUBE deliver it into space. So before you embark into space, you should ask these questions. Why go into space? How does space strengthen our industrial base? How does it improve our agricultural base? How does it strengthen national defense, improve our workforce, and improve R&D capabilities? You have to have good reasons for going into space. So these questions are relevant to countries of Africa because today, any country in Africa can build its own satellites and get them into space for the specific purpose of helping its own citizens. But this slide is not apparent to a lot of people. There's been a massive game change in the space industry. So the policymakers in Africa have to be aware of this development, which is on the next slide. So we have shifted from old space to new space. It's a paradigm shift. Old space, only the big countries could participate due to the enormous cost. Development time took 10 years, etc. But now we have new space. Example, this 1U by Guatemala, it weighs 1 kilogram, only $200,000. So unfortunately, older people who occupy management only are cognizant of old space, whereas new people tend to know more about new space. And this is really a massive game changer. So this is significant for Africa. So with the advent of new space, Africa can now design, develop, build, and test, launch its own Earth observation satellites. So the important question to ask yourself, why should I buy my own satellites if I can, one, buy satellites or buy satellite data from commercial services? So to fully exploit space for national profit, you have to do it yourself. If you buy a satellite, it does nothing to develop your engineering workforce. And all problems are local. This slide is from Professor Jordi Potswari. That's why buying commercial satellites is a bad idea, because you have specific local problems and you should address that with your own custom-built satellite. For example, problems of all agriculture are all local. If you want to precisely attack your local problems, then you need to design and build your own satellites. There's no way around this. You don't have to, I don't strongly recommend satellites that take photos, because that you can buy on a commercial basis. But there's still many other applications for small nations to consider. This is just one example. It's from Irazu, the first satellite of Costa Rica. The mission of this was simple, just store and forward. So as a satellite flies over a remote area, the data is beamed up to the satellite, and then it flies over a central ground station, and the data is sent back down. So you can collect data in places that have no information infrastructure at all. So I have presented two examples of 1U CubeSat so far. The first satellite of Guatemala and the first one of Costa Rica. What they have in common, they were designed and built domestically. Both were funded domestically. Both were deployed by the JAXA's JSSOD system, which you'll hear more about today. And both created in-house human resources for future space projects. The last item is the most important part. So I come to the central thesis of my presentation today. Why you, as a non-spacefaring nation, should build a 1U CubeSat to become a sustainable member of the global space community. So point number one, if you wish to be a serious and long-term actor in the space industry, then it is imperative that you develop human resources in the space sector. You have to have your own human resources. Number two, learn by doing. Barriers for new space have come down, but to understand the advantages and disadvantages of using space to help your people, you have to master the following: selecting payload missions, designing a satellite for those missions, fabricating that satellite, testing that satellite, and so on. And point number three, as a first satellite for your country, a 1U CubeSat is a very, very reasonable proposition. It's not that expensive. It can be done quickly, under 2 years. It can be reliable. Scores of nations have done it already. It's easy to get into space. So in any case, with the first satellite, you can train your first generation of space engineers. They will acquire the confidence and skills to develop more and more useful satellites for your country. But you have to start somewhere. The bottom line is this: capacity building. Maybe the first satellite is attractive because it's your first satellite, but you have to remember that is not the goal. The goal is to develop your human resources. That's why you need to do it yourself. If you buy one, then you learn nothing whatsoever. Next, I'm going to talk about Japan and how we help non-spacefaring nations with capacity building in many ways. Time is limited, so I will only mention these three examples: JAXA, UNISEC, and the place where I worked before, QTech, Kyushu Institute of Technology. So there's capacity building by JAXA. Working with UNOOSA, JAXA is providing a KiboCUBE program. I will not talk about this in detail because it will be covered by other presenters today. The bottom line is you have a chance to get your satellite into space with a free launch by JAXA. In support of this, JAXA has developed a series of free lectures in English by experts in space engineering. Please view this YouTube video later on. And you can access all these lectures using the web link shown below. And then there's capacity building by UNISEC Japan. They do all these activities. Again, please view this YouTube video later on. You probably have heard of this, CubeSat. It's actually occurring right now in Japan. It's in progress this month, August. Its CLTP-11 is now underway. And they now use the HeptaSat as the basis for their training. It used to be this can-shaped satellite. And finally, the flagship programs of QTech are PNST and the BIRDS program. So this is very important. It's the PNST opportunity. Each year, 6 scholarships are given away, 3 PhD, 3 masters. This is done through the UN Office of Outer Space Affairs. So if you go to their website, you can apply. Applications just opened and they'll close towards the end of this year. Definitely give it consideration because we're taking 6 every year and we've done this since the year 2013. And then you join this SCIC, Space Engineering International course. So again, please download the presentation file and look this over carefully. A few short words about the BIRDS program, which I was heavily engaged in. So we had BIRDS 1, 2, 3, 4, and 5. Many African nations, Ghana, Nigeria, Uganda, Zimbabwe. Using BIRDS, they put their first satellite into space. These are photos of BIRDS 1. These are BIRDS of 5. Zimbabwe and Uganda were part of this. These 3 satellites will go up within a few weeks from today. I believe today we have one representative from Uganda in the audience. And this was the handover of BIRDS 5 satellites to JAXA in May of this year. Concluding remarks, the only way young engineers can learn how to build a satellite is to build one with their own hands. Book learning or classroom learning does not work. After going through a BIRDS project, engineers gain the confidence to build satellites by themselves. This is the most important thing, confidence, right? If you're starting from scratch, you don't have that confidence. But if you physically build a satellite from A to Z with your own hands, then you will have the confidence to build the second one. If your country wants to join the space age, the best way to train your engineers would be some methodology similar to BIRDS. That's the end. I thank you for your attention.
Thank you very much, George, for the keynote. I think it really illustrated why we're here today to talk about capacity building and to talk about why it's important, why it's amazing to work on CubeSats as the first. So, hello again. My name is Hazuki, Hazuki Mori. I work at the United Nations Office for Outer Space Affairs, and I'd like to talk about our Access to Space for All initiative. At UNOOSA, we do a variety of capacity building activities, but today I'd like to focus on space technology capacity building. And KiboCUBE and PNST, the ones that were mentioned earlier, are under this Access to Space for All initiative. So this initiative is called Access to Space for All. It's to provide research and orbital opportunities for UN member states to access space and to make sure that the benefits of space are truly accessible to all. And you can see our core values on the left-hand side. The first thing is we provide the possibility of developing hands-on capabilities from A to Z. What we mean by A to Z is starting small with easier skills and moving on to more complex skills. The second part is we provide cutting-edge skills for jobs and other opportunities. Going through this gradual learning path, we provide the opportunity for applicants to really get cutting-edge skills. The third point is we foster international cooperation. So we, the United Nations, we work with our spacefaring partners and of course the flying developing nations. So you will have international experience. And last but not least, it has a very strong impact to the countries and that are participating, and of course the young generations. And on the right-hand side, you see the Sustainable Development Goals. We are focusing on 3, which is quality education, and number 8, which is promoting inclusive and sustainable economic growth, and the last one is innovation infrastructure. So this slide shows the impact of the initiative. As you can see, when teams join the initiative, there's more opportunities for media coverage, there's more opportunities for new partnerships and new opportunities. I noticed yesterday when I went to Espita that after they won KiboCUBE, they have a new facility. I mean, they have a new AI and digital center, I believe. So this is also thanks to being selected as a KiboCUBE awardee. This is the structure of the initiative. We have 3 main goals. So we have 3 main tracks with 3 main goals. The hypergravity and microgravity track is built for building capacity for conducting experiments on orbit. The satellite development track is building capacity that enables the development, deployment, and operation of the satellite, so the whole life cycle of the system. And the space exploration track is really going beyond LEO, beyond GEO. And to support these tracks, we have 3 different components. It's the hands-on component, the tools component, and education component. So the hands-on component is the actual hands-on research and orbital opportunities that we have. The tools component, I will explain a bit more later, but we have compiled a list of software, open and accessible software and tools that people can use to actually utilize when they're doing their hands-on opportunities. And then we have the education component, which is the baseline of actually using the tools in the tools component. And of course, I'm taking part in the hands-on component. So this is our hands-on component. As you can see under the hypergravity and microgravity track, we have 5 opportunities. On the left-hand side, you see our on-ground opportunities. Drop test is utilizing the Bremen drop tower to conduct a drop tower experiment, microgravity experiment. The second one is HyperJust. This is actually open for applications right now. So if anyone is interested, please take a look at our website. This is an opportunity to conduct hypergravity experiments at the Large Diameter Centrifuge Facility at ESA. So this one's open right now. And on the right-hand side, you see our on-orbit opportunities, such as using the ISS Bartolomeo platform, the Chinese space station, of course, the Dream Chaser vehicle. And today I want to focus on the satellite development track, especially on, of course, KiboCUBE, but I just want to explain that we have other opportunities as well. We work with our colleagues at UAE to provide a payload hosting initiative, PHY. This is a PHY-U slot within a 12U satellite. And then we also work with the Italian company Avio, utilizing their Vega C for a 3U opportunity. But today, of course, we're here for KiboCUBE Academy. I will be talking more about KiboCUBE, which is a 1U opportunity. And for people here, you can see we have this space exploration track. We have one opportunity called ISOScope, which is the provision of telescopes for astronomy. But as I said, we want to have more opportunities that will help you get beyond. So how is, well, basically George explained it all, but what will, making a CubeSat, utilizing CubeSat, operating a CubeSat bring to you? How is it relevant to your country, to your region? As George really explained, CubeSats offer a large variety of applications with CubeSats and of course, gradually going up to bigger satellites. you can do a lot of things with the different sensors, with the different things that you put on board. CubeSat developments can be the first step for a country in the acquisition of the skills and know-how you need to develop a space program. And of course, CubeSats are becoming more and more affordable to develop and of course to launch as well. And it represents an achievable entry point for space activities. So what is KiboCUBE? I hope all of you know what KiboCUBE is because you're here, but it's a cooperation program between the United Nations Office for Outer Space Affairs and Japan Aerospace Exploration Agency. It started in 2015, and as I said, it's under the Access to Space for All initiative. The aim is to provide educational or research institutions from developing nations and economies in transition with opportunities to deploy a 1U CubeSat. And they will develop it, manufacture it, hand it over to JAXA, and then JAXA will take care of launching it up to the ISS and deploying it. So why KiboCUBE? There may be some programs that are kind of similar to KiboCUBE, but we think that KiboCUBE is very special in the sense that first, it's very cost efficient. JAXA will bear the cost of the launch of the CubeSat and the deployment. And when you deploy something from the ISS, there's astronaut crew time, which is involved, but that part is all free. So what the flying teams have to do is just build their satellite and bring it to Tsukuba Space Center. So it's really cost efficient for a developing country that wants to make the first step. Second of all, it's really friendly. It's a really friendly environment for launch. When we take it to the ISS, it's part of cargo. So it's really wrapped nicely. It's like DHL, you take it up to space, someone takes it up to space for you. And there's lower vibration. So your CubeSat will be carried in better conditions compared to being on a piggyback of other launchers. And last but not least, there's a lot of support from UNOOSA and JAXA. So there's a lot of technical support from JAXA and the other Japanese contractors that are supporting JAXA. And of course, we at UNOOSA, we will provide you with administrative support. So you have a whole package of this support. I just want to focus on some of the awardees that have successfully deployed their CubeSat. The first one is from Kenya, and the achievements are amazing. They downloaded more than 300 images, which is surpassing the initial expectations, and it really accelerated the creation of the Kenya Space Agency. And after joining KiboCUBE, the Kenya Space Agency has been really active with us. They're participating in access to space for all opportunities, such as Bartolomeo. They work with other African countries to put up a payload on the Bartolomeo platform. And of course, they're working on the ISOScope program as well. The second awardee is Guatemala. Their satellite was amazing as well because it involved more than 100 students in the program, and it was developed, like more than 70% was developed in-house, which is an amazing step for the first country. And they did an amazing job conducting successful outreach activities. They worked with the media and involved a lot of the students, the young generations in the country. It was a really big thing. The third round awardee was Mauritius. This was deployed last year. This was one of the first small island developing nation SIDS to develop a satellite. And they did an amazing job conducting successful outreach activities as well. They did a lot of work with the schools and universities to do antenna workshops so that all the students can access to MeerSat-1 as well. And last but not least, we deployed the satellite 2 weeks ago of Moldova, and the Prime Minister and other ambassadors attended the event. It was very exciting, and we're really hoping to get more images and more things coming on from this satellite. And with this, you can see the upcoming CubeSats. We're very excited to have the Indonesian one probably being deployed later this year. And then we have 3 more coming up. And of course, we have one from Tunisia, and we're very excited. So besides the hands-on component and KiboCUBE, in the satellite development truck, we have a thing called the tools component, which is on our website. And you can find a lot of different softwares that you can find that are free and open source that you can use that can really help you through the hands-on capacity building and especially going through KiboCUBE. And then we have the education component. We're providing a bunch of webinars through KiboCUBE Academy like this. We have fellowships. So the one that George mentioned earlier through the keynote, we work with QTech and the Ministry in Japan for the PNST program, the postgraduate study on nanosatellite technology, which he explained earlier, but we fund 3 students for masters and 3 students for the PhD to actually study in QTech, and you get to go through the whole life cycle of satellite development. And I know there's a few alumni in the room, and of course, George can address you more about this, but it's an amazing program and it's open right now for applications. And of course, we do workshops. We have one coming up in Paris along with the IAC as well. And KiboCUBE Academy, I don't know how many of you have actually seen our other webinars, but basically the aim is to provide theoretical knowledge to really develop, operate, and utilize small satellites. And we did season 1 in early 2021, and then we did season 2 later in the year. And you can see the 21 pre-recorded videos that are also there. So we did live webinars, but we have pre-recorded webinars. And the ones in bold from 16 to 21, they have been uploaded very recently in August. So they're new and they're fresh. So please make sure to take a look at them. So with this, I would end my portion of the webinar, and I will give the floor to my colleague from JAXA, Mr. Tatsuhito Fujita, to talk about JAXA, the ISS, the JSOD, and all the other opportunities they have.
Hello, good morning and good afternoon and good evening in the world. I am Tatsuhito Fujita. I'm engineer of JAXA. I'm in charge of development service of small satellite like CubeSat from International Space Station. Today, I would like to introduce this development service. Okay. So at first, I would like to introduce International Space Station, ISS. ISS is a huge mount construction located about 400 kilometers above the Earth. So the size of ISS is one length is 100 meters. Another one length is 80 meters. So the size of ISS is like the size of the football court. Okay, so big structure, and 15 countries participate in the ISS program. United States, United Kingdom, France, and there are various Europe, Russia, and Japan. Okay, and Japan Japan developed the Kibo. Okay, so Japanese experimental module. So in Kibo, various of equipment of test is located. So in Kibo, test like the protein or animal and observation or something is carried out. Okay. Sorry. Oh, sorry. So next, I show the KiboCUBE. No. Next, I show the Kibo exposure facility. Kibo exposure facility has the many. Sorry. Unique capability to conduct various space experiments in exposed facility, and them okay. And so in this exposed facility, the large size equipment is set like this. Okay, so the mission of this equipment is like the Earth observation and observation of astronomy. And another equipment JAXA prepared IVA replace small exposed experiment platform IC. If using IC, you can carry out the small size of test like the the test of the exposed space environment, and the now using IC, so the camera is set. We can operate the camera in IC. Okay, and now today I want to introduce development of a small satellite. So we use this is James Small Satellite Orbital Deployment. We call JSOT. Okay, so using JSOT and the small satellite like CubeSat can be deployed from ISS. So next I show the JSOT. So JAXA can operate the satellite deployment missions from Kibo from 2012. By August 2022, 65 satellites have been successfully deployed from JSOT. Okay, and the JAXA has selected Space PD and St-Pierre Aerospace as a service provider. These images are the deployment of satellites. Okay, using JSOT. So next, I show the small satellite category. Small satellite is categorized microsat and nanosat and picosat. Okay, so today I bring this model is picosat. What is called a CubeSat. Sorry, yesterday I had the news that I was arrested because of this CubeSat, but I'm not arrested. Okay, this is not right. Okay, yeah, you fake. Yes, okay, okay. So this CubeSat is we call 1U size. So one length is 10 centimeter. Okay, so the weight of this CubeSat is about 1 kilogram. Okay, so the merit of the CubeSat is one is the extremely low cost. Okay, so usually satellite is smaller, the cost is smaller. Okay, so of course, new players are welcome to join, and great opportunity for education tool and challenge mission. The cost depends on the mission, but usually if the mission is simple, the cost of this CubeSat is about $100,000 or $200,000. Okay, so next merit is short time around the life cycle. Okay, of course, so satellite is smaller, the time of development is short. Okay, so usually the time of development of this CubeSat is about 2 years. Okay, so college student can experience for development cycle using this CubeSat, and curriculum can be standardized as a sustainable program, and quick return on your business investment technology demonstration. Okay, the third merit is a cost-effective method for various missions. So even if this satellite is very small, but this satellite has a camera. Okay, so this satellite take photo of the Earth or the astronaut, so star. Okay, so practical remote sensing data can be obtained from a small satellite like this. Okay, so next I show the specification for JSOT platform. Okay, so using JSOT, the small satellite, like the CubeSat, 1U or 2U is connected, 1U is connected, and 3U or 6U can be deployed from ISS, and even 50 kilogram satellite can be deployed from ISS. Okay, so satellite mass is the requirement of weight is less than 1.33 kilogram per 1 unit. Okay, and in the case of 50 gram, of course, weight is less than 50 kilogram. Okay, So altitude, orbital altitude is 380 or 420. Of course, depend on the orbit of International Space Station. So inclination is 51.6 degree. Of course, this inclination is the same of ISS. Okay, and the deployment direction is okay. This image. So the satellite is deployed in the direction of like this. Okay, this red area. And so the merit of ISS is lower vibration environment. So in ISS, lower vibration environment are provided since small satellites are stored in the softband, okay, and carried to the ISS together with other cargo. So next, I show the JSON case. Okay. So this is JSON satellite install case. Okay. So satellite of 1 or 3U or wide 6U and 50 kilometers can be deployed using this JSON case. But now this model is for the 1 or 3U of CubeSat. Okay, and the satellite can be installed. This one. Okay, and the on the ground. Okay, so usually the installed satellite is carried out in scuba space. Okay, and the crew mount satellite install case on MPEP inside Kibo. MPEP is the interface between robot arm and this case. Okay, this one, this material. Okay. So JAXA can provide another JSON case. This is number 2, JSON-R. Okay. In JSON-R, so satellite of 1 or 6 can be deployed, and satellites can be installed in satellite launch case on the ground and launched. And the crew installs satellites in satellite deployment case and mount satellite deployment case on MPEP inside Kibo. So satellite install case can be kept in Kibo and reused again. So JAXA uses 2 types of JSON case. So next, I show the achievement of JSON. So 40 CubeSat from 27 countries were deployment using JSON. Zimbabwe, Uganda, and Indonesia satellite will be launched and deployment this year. Okay. So Mori-san said, yeah, of course, 2 weeks ago, the Moldova satellite was deployed from ISS. So next, I show the capacity building through JSON. Okay. JAXA has provided the opportunity of satellite deployment to various countries as the great way for sharing the values of ISS Kibo for the purpose of enhancing satellite deployment and operation technology. Okay. So JAXA launched new comprehensive capacity building measures to provide the educational programs and sustainable satellite deployment opportunities, which finally contribute to the SDGs Goal 4, 8, and 9. So formally, UNOOSA Mori-san explained KiboCUBE and KiboCUBE Academy. And JAXA provided another measures is JCube. So I show the drawing of JCube. So JAXA launched the new fee-based satellite deployment initiative, which is called JCube from 2021. Okay. So this JCube, JAXA allocated up to 6 satellite deployment opportunities for 1U to 3U satellite per year. JAXA provides the 2 sets of frameworks, international collaborative framework and the Japanese domestic challenge framework. For the international collaborative framework, satellite deployment opportunities for the space emerging country provide for more challenging and advanced missions with a collaboration with Japanese universities. JAXA signed an agreement of JCUBE with UNISEC Japan in April 2021. So you can find the outline of JCUBE of the following website. So if you want to know the details of JCUBE, please check this website. And 3 satellites were selected in the international collaborative framework, and 2 satellites were selected in the collaboration with Japanese universities test year. So I hope people who participate in this KiboCUBE Academy, so I hope so the people who participate of the KiboCUBE Academy, so working in space development in the future. Okay, so my presentation is finished. Thank you very much.
Okay, thank you very much, Fujita-san. I'd like to open the floor to questions and answers. I see some online as well, but I'd also like to start on site here. So does anyone have any questions in the room from Tunisia here? If so, please raise your hand and we will go around the floor with the microphone. And if not, maybe I can start with the online ones. So I think this one is addressed to you, George, because you were mentioning old space and new space. There's someone asking what the difference is between old space and new space. So maybe you can give a description of what old space and new space means in your definition.
Okay. Old space refers to, say, the Apollo era, where everything is large, everything's expensive, everything takes 5, 10, 15 years to develop. That's old space. And unfortunately, many people still think that's what space is all about. But because of rapid technological advance, I would say the smartphone, the thing you have in your hand right now, had a major impact on this because of the volume. Billions of these phones are created. It vastly brought down the cost of software and hardware. That has enabled new space. So new space means inexpensive satellites, under $1 million, takes less than 2 years to develop. They're very small, they're not big anymore. So this is the fundamental difference between new space and old space. The bottom line is probably if we were still in old space, Africa would still have nothing to do with space. However, with new space, Africa can do a lot of things now in space because of new space. How's that?
Fantastic, thank you very much. One more question from the Q&A online, and this is to Fujita-san. If you can give him the mic. So the question was, do CubeSats only operate in low Earth orbit? So maybe you can explain about the orbit of the KiboCUBE and the JAXA deployed satellites.
That's true. So the almost the orbit of CubeSat from ISS is the same of orbit of ISS. So of course, satellites have the thruster in the change orbit. Satellite orbit is a little bit higher, but usually CubeSat, the orbit of CubeSat is in low Earth orbit. Okay.
Okay, thank you very much. And just to add, my colleague Wenbin has put it in the chat for this question as well, but there are small satellites not only in low Earth orbit and different orbits. So it doesn't mean that CubeSats can only operate in low Earth orbit. But for KiboCUBE and for the deployments from the ISS, it's in low Earth orbit. Okay, does anyone have any questions from the floor? I saw one. So can you give the mic to this gentleman here? Fujita-san, maybe you can give them the mic.
Thank you, sir. I present myself. My name is Anis Chapchot. I represent the National Agency Frequency. And at the same time, I'm the president of National Association of Radio Amateurs. My question is in the 60. First, I would like to thank you for the interesting presentation. And my question is now the technology has become more easy. I will take the example of in the 60 and the 50 and 60 years in the last century, we cannot imagine the personal computer because at this moment the computer it was very big, very large, and very costly. To imagine the personal computer, it was something of the future is not possible to do. And now, if I ask, what do you think about in the future about the personal satellite? That can we, in few years, I don't know how many, that imagine that every person or every people can have his own satellite on the Earth. It's possible.
That's an interesting question. Maybe I can address it to George.
Okay. Yeah, I understand the question, but there's some limitations. First of all, one subject we have not discussed today here is space debris. So if people start sending up satellites, this will aggravate a problem called space debris. And the second problem, the other problem is you need frequency. It's a scarce resource. So you have space debris and frequency limitations. So with these two constraints, I'm not sure how far your idea will go.
Just to push the imagination of it.
Yeah, no, thank you for the interesting question. And if I may add to that, space is becoming an environment that we need to preserve. So in the United Nations itself, we're seeing space become an environment, and we really value long-term sustainability regarding that. Would Luke like to add something? Yeah. Can you give the mic to Luke?
Thank you. There's a third complexity to that. Launching satellites is under international treaties, and the launching state is recognized as the authority, and they have to register the satellite and all the statistics. So having individual in that is an additional constraint. So come back in a few years.
No, but thank you for raising this question. It brought up a lot of things that we really need to consider when we talk about small satellites. I saw another question. I think, sorry, I think he had it first. Can you give him the mic?
So, my name is Charles Mori from Kenya. My question is to George in terms of whether in the resources that are available for the KiboCUBE Academy, where anyone can use, whether any person can use that without having to worry about copyright. Then on an issue that you mentioned, he indicated that the one you provides a good entry point for countries, and I wanted to hear his comment in terms of what would be the next step, because quite a number of countries have already launched 1U, 2, 3U satellites, and maybe now the push would be towards constellation, and there was an indication of that could be an area that has a lot of potential where we build on the capacity that we build. Then the other bit is on, if you can comment on the infrastructure, because one of the challenges that we have within the developing countries is we train people in developed countries, and when they come back to the countries where they're supposed to work from, they don't have the infrastructure to be able to continue that technology. Thank you.
Okay. There were several questions there. I think the first question was about KiboCUBE Academy, and I'll let Mori-san answer that later. So, what happens after 1U? So that the point of the first 1U is to create some human resources. Whether that's done in Japan or other, doesn't matter. The point is these guys or these men and women should go back to the country and start building the second, third, and fourth satellites. And often these become 3U or 6U, okay? But you have to start somewhere. I think 1U is the right place to start. You don't want to start with 3U. That's too ambitious as a first satellite. I think later on you asked about infrastructure. Yeah, that's a difficult problem, but that's something the individual countries have to resolve on their own strength, you know. There's only so far that UN and countries like Japan can help you, and then as far as internal and domestic infrastructure, that's really up to you. So Mori-san, can you continue?
Yeah, I think a lot of that will be mentioned tomorrow in tomorrow's workshop, and I think that will give you more high-level discussion. So I'll leave that to my colleagues that will be presenting tomorrow. I had one more question from the floor, and then we'll close up because we are running out of time. So
please, yourself, Tunisian diaspora. My question. For new satellite, where is the opportunity for Tunisian development country in free internet? Can new satellite help students in new internet en France? Est-ce qu'on peut, avec le new satellite, avoir l'internet gratuit?
I don't speak French, so maybe I'll give it to my boss over there, to Luke.
Just he asked if with the new satellite we will have a free internet. This is the question.
And, yeah, if you.
I can give elements of answer. Not considering free or paying, there's a lot of effort now to promote satellite-based telecommunication for global coverage of internet. This is also related to private sector development also. So this is coming because there are limitations with the regular internet services where not every area can be covered. So there's a lot of push for that. And obviously the small satellite constellations that are being sent by private entities now will answer some of that. Then the rest is market. Yeah, so being free or not free would be developing in the private market. But the main thing is to provide good coverage at the speed of our need.
It also depends on the size of the satellite. So when we talk about KiboCUBE and 1U satellites, there's not much you can put on because there's not much size, right? But as the satellites grow bigger, there's more payloads that you can put on, more sensors, and you can do different things like having a camera or having communication transponders and all. So it really depends, but the first step you have to go into is being able to build a satellite. So after that, I think Tunisia can have more discussions of what you can actually do with the space technology. I hope this addressed your question, and I'd like to take a few minutes of break and then move on to the next session. I saw some questions in the online chat version, but actually some of them will be answered by our professors that will be presenting next. So if you still have questions, you can of course address them, but I think a lot of them will be answered in the next part of the session. Okay, so thank you very much for coming back. We will start the next session of KiboCUBE Academy, and we will be talking about CubeSat technologies. This part will be done from our professors in Japan in UNISEC, and the first speaker is from Tohoku University, who is the associate professor and doctor, who is Dr. Toshinori Kuwahara. So I believe Dr. Kuwahara is already connected, so I will give him the floor. And I also just want to mention again that the presentations are already on the UNOOSA website. My colleagues will be sharing it in the chat area for the online people. For the on-site people, please go to UNOOSA, our main website, go to Access to Space for All, and then to KiboCUBE Academies. And if you can't find it, please contact me later. Okay, I would like to give the floor to Dr. Kuwahara.
Okay, thank you very much for the introduction. Can you hear me?
Yes, we can hear you.
Okay, so again, hello everyone. So thank you very much for attending this KiboCUBE Academy hybrid lecture event. So I'm very honored to give you this lecture today. I hope you enjoy the lectures. So the first lecture is about CubeSat technology. So I hope you can also see the slides there. Okay, so I'm also seeing that floor from the behind. So thank you. So first of all, my name is Toshinori Kuwahara, Associate Professor at the Department of Aerospace Engineering of Tohoku University, Japan, and also the chairperson of UNISEC Japan. So my research topics are space development, utilization, and exploration by small spacecraft technologies. So these are the exemplary, small satellites I have been working on. So now let's start the lecture. So here is an overview of this presentation. I will start with an introduction to space systems, followed by introduction to CubeSat systems, definition of satellite subsystems, CubeSat payload systems, and finally, I conclude my presentation. The first chapter is the introduction to space systems in general. So on this slide, I'd like to introduce the major satellite application fields. So there are a wide range of satellite applications which we can benefit from. The first category is the Earth observation. These include meteorological observation, oceanographical, geographical, and coastal area observation, atmospheric observation, and disaster monitoring and prevention, and so forth. So some of them are illustrated in these beautiful pictures. Forward C to JAXA. The second category is communication. Satellite broadcasting, telephone, internet, etc. belongs to this category. And the third category is navigation. So these are global navigation satellite systems and traffic management systems such as air, land, water, railroad, etc. And the final category on this slide is last but not least, the science applications. So starting from the astronautical observation, microgravity experiments, such as medicines, pharmacy, etc., and space exploration, such as moon, asteroids, planets, and deep space. So on this slide, I have also listed some pictures of exemplary CubeSats on the right side. Even though the CubeSats are very small, nowadays they are also utilized in many of these application fields. So first of all, we need to understand about satellite orbits when we talk about space technology utilization. So there are many different types of satellite orbits. I have illustrated several typical satellite orbits in this figure. The blue one is the geosynchronous orbit, and the green one is the sun-synchronous orbit, and the red orbit is the ISS orbit. So this ISS orbit is tilted with an inclination angle of about 51.6 degrees, as discussed before. The altitude is about 400 kilometers, and because the orbit altitude is low, the ISS orbit also belongs to low Earth orbit, or also known as LEO. So satellites released from the ISS will also follow a similar orbit as the ISS. So unlike the sun-synchronous orbit, the sun illumination condition of the ISS orbit changes with the time. So you need to consider several important effects on your satellites, such as power generation and thermal control, etc. So for the satellite operation, you need to understand the characteristics of satellite orbital motion. So I'll explain these one by one on this slide. So satellites in ISS orbit rotate around the Earth about 16 times per day, which means that one revolution of the orbit takes about 1.5 hours or about 90 minutes. So Earth also rotates once per day. So as a result, the relative velocity between the ground station and the satellite is on the order of about 7.7 kilometers per second. So the satellite operator has a limited amount of time for communicating with the satellite. And this also depends on the geographical position of the ground station. The satellite operator sends commands to satellites from the ground station and receives telemetry data from them, in most of the cases via radio frequency communication. For satellite operations, the following aspects must be considered. So satellite orbit and mission lifetime, communication system, ground station, link budget design, operational phases, and regulations. So satellites orbiting in high inclination orbits can cover a large portion of geographical area on Earth. Here I have an animation of satellites on the ISS orbit and its ground track. So you can now understand how the satellite can cover a portion of Earth due to the combined effects of satellite orbital motion and Earth rotational motion. So this feature of global accessibility can be utilized for Earth observation. So you can conduct periodic, frequent observations of ground area under the satellite orbit, and communication. So you can have communication contact with ground station in the visible area from the satellite. Environmental measurements. So you can measure the space environment such as magnetic fields, radiations, and so on. And the higher orbits can have a wider field of view, and the lower orbits can facilitate higher ground resolutions of Earth observation. So satellites are basically continuously falling toward the Earth. So this free fall microgravity environment can be also utilized for experiments related to material science, bioscience, medicine, etc. The space also provides unique environments such as vacuum, high radiation, strong ultraviolet light, cold and hot temperature, and existence of atomic oxygen and plasma, etc. So if you think about space utilization, you can consider these important characteristics of the space environment and space systems. So let's examine the ISS orbit in detail. So these are the parameters of the ISS orbit. The orbit altitude is about 400 kilometers. As I said, the inclination is about 51.6 degrees. The orbital period is about 91 minutes. So it is also very important to know that the orbital altitude of the ISS is changing by about plus or minus 20 kilometers due to the effect of atmospheric drag. The higher the initial orbital altitude of your spacecraft is, the longer the mission lifetime you will have. As I already mentioned, the CubeSats deployed from the ISS stay in almost the same orbit as the ISS. So slight differences in initial relative velocity and the different material characteristics, such as the mass and shape of the spacecraft, that makes the CubeSat separate from each other into different orbits. So the second chapter is Introduction to CubeSat Systems. So on this slide, I'm showing the comparison between the traditional large satellite and the new small satellites. So this is a large satellite of JAXA, AO3. And these are exemplary small satellites, and this is me. So let's take a look at these key parameters: the mass of satellites, the cost, and the development time. So compared to larger satellites, small satellites are characterized by having small mass, low development cost, and short development time. So in addition, larger satellites need dedicated launch vehicles, and because they are very expensive, they are required to be highly reliable and cannot assume a lot of risk. And also, though the performance is very high, the frequency of observation is low because you cannot launch several large satellites due to the cost issues. So on the other hand, thanks to the characteristics of small satellites, there are several key benefits. So first of all, the small mass means frequent launch opportunities. So you can launch many of them by a single launch. And you can also launch them as piggyback satellites together with the main large satellite. And secondary, because of the low cost, you can try challenging missions And also you can establish large constellations and networks of small satellites, which could provide very frequent observations. And thirdly, because of the short development time, you can utilize brand new technologies. So thanks to these features, small satellites are regarded as suitable platforms for space education, as well as the rapid new technology demonstrations. So this slide illustrates the mass categories of small satellites. The smallest category is the pico satellite, which is ranging up to about 1 kilogram. And the next larger category is nano satellite, ranging up to about 10 kilogram. The third category is the microsatellite, up to about 100 kilogram. Then the last category in this slide is the small or medium satellite, ranging up to about 1,000 kilograms. So when you talk about CubeSats, their mass category is now ranging from about the pico to microsatellites, as illustrated with this red line. And they are becoming bigger and bigger. So I have already shown you several pictures of CubeSats. So one CubeSat is a 10 centimeter cube with a mass of up to 1.33 kilogram. So some standards are available and I have listed them up here. The first one I introduced is the CubeSat Design Specification Lab 113, organized by the California Polytechnic State University. So it is publicly available under this link. So this standard provides a basic idea of CubeSat. So I recommend that you are informed about it as the first steps. So there are several more working documents available in the community. The second one I introduced today is the CubeSat system interface definition, organized by UNISEC Europe. And this standard suggests interface definition for the internal electrical components of CubeSats. This is available here. The third one is the ISO standard. Standard for space systems about CubeSat is established in 2017, which addresses CubeSat deployer, and related verification of assurance and quality terms and metrics. The fourth one is the GEM Payload Accommodation Handbook, Volume 8. So I think this is the most important and relevant document for you when you apply for launch opportunities through KiboCUBE Academy. So GEM stands for Japanese Experiment Module, which is another name of the Kibo module. So both English and Japanese versions of this revision is available here. So on this slide, I have summarized the CubeSat deployment opportunities from Kibo. So Kibo provides options of JSOT in 3 different forms. So 3U, long 6U, and wide 6U. So consequently, there are these kinds of form factors of CubeSats, which you can utilize for your own projects. So they are 1U, 1.5, 2, 3, 4, 5, as well as long and wide 6Us. So it's possible that your satellite is stored into the pod together with satellites developed by other project teams. So among the possible form factors of CubeSats, the 1U CubeSat is especially the best platform to learn essential engineering skills and technologies for satellite development and operation at the first step. So these pictures below illustrate the outer appearance and internal components of a 1U CubeSat. So 1U CubeSat is the simplest implementation. So larger CubeSats can be utilized depending on the technology level and the mission requirements. So a smaller format is mainly for fundamental functionalities, and larger formats are required for missions with which requires larger sensors, accurate attitude control, and a large amount of data transfer, etc. So although the form factor is very small, CubeSat components are getting more and more sophisticated. And nowadays, there are a lot of commercial CubeSat components available in the market. So these are some of the sample commercial products. So with the help of these commercial products, you can construct some components by yourself, and you can buy the remaining components from the markets. So in this way, you can now start using CubeSat very seamlessly from scratch and can gradually develop your own technologies. So in the following chapter, the definition of satellite subsystems, I'd like to explain about the general functional classification of satellite components together with the example of CubeSat devices. So first of all, the functionalities of a satellite system can be classified into several subsystems, which are closely related with each other. So this slide tries to illustrate the relationships. So this is a typical classification into subsystems. They are the power control system, communication system, command and data handling system, structure and mechanism system, thermal control system, attitude control system, and orbit control system for advanced missions, and then payload system. So the attitude control system is sometimes also referred to as the attitude determination and control system, as it needs a determination of the attitude as well before you control it. The attitude control system and orbital control system are sometimes treated as a single subsystem as attitude and orbit control system. So as illustrated, I have put the payload system in the middle on the top of all the subsystems. I wanted to emphasize that the payload is representing your satellite mission objectives, and all the subsystems exist to fulfill the required functionalities to achieve the mission objectives with the payload. And also all subsystems except the payload system are denoted as the satellite bus system, with the payload being the passenger among the other subsystems of the bus. So though all subsystems are equally important, I will try to explain from the most essential ones, in my opinion. The first subsystem I pick up today in this sense is the power control system. So a power control system manages power generation by solar panels stretched into secondary rechargeable batteries and the distribution of power to the satellite components. So this combination of components I mentioned, the solar cells, batteries, and power control computer, can be regarded as a power control system. The power control computer is usually referred to as a power control unit or power control and distribution unit. So sometimes the power control unit and the power distribution unit can be separate components. And PCU and or PCDU sometimes convert the supply voltage to the satellite components inside, as illustrated in this diagram. So power control system shall be highly reliable as compared to other onboard components. The size of solar cells and the capacity of the battery shall be determined based on the power consumption requirements of the satellite mission. These are the pictures of exemplary power control system components: solar cells, batteries, and some power control units. So here I have an example of power control system. This is a 2U CubeSat Raiko, so developed by Tohoku University. This satellite is the world's first CubeSat released from the ISS. So this table summarizes the specification of the power generation, power storage, and the power consumption of the CubeSat as the example. The next subsystem I pick up is the communication system. So as the satellite operates remotely in space, information exchange through communications are indispensable to make the mission of the satellite meaningful. The communication throughput, especially for the downlink in general, determines and limits the entire performance of the satellite system itself. So for high-speed communication, higher electrical power is required, and the temperature of the transmitter increases during the communication. The receiver shall be ideally powered on at all time so that the satellite doesn't miss any commands sent from the ground station. The transmitter can be turned on and off according to the ground contact schedule. So this is important to save electrical power for the satellite. The communication systems also require an onboard antenna. So low frequency radio waves, that is a longer wavelength radio waves, require a larger antenna. So VHF and UHF frequency bands are widely used for CubeSats, and they require an antenna with larger dimensions. So high frequency bands such as S-band and X-band, which are also used for high-speed communication for CubeSats nowadays, require a smaller antenna. So it is often the case that a Yagi type antenna is used for the low frequency bands, and the dish type antenna is used for high frequency bands for the ground station, as illustrated in this figure. So the next subsystem is a command and data handling system. So the command and data handling system, often denoted as C&DH, it manages data handling, components commanding, monitoring, data storage, signal processing, and error handling inside the satellite. So certain levels of autonomous functions need to be implemented in C&DH so that satellite can survive in the space environment. A high level of reliability is required for the C&DH computers. So when the computer fails to function correctly, due to, for example, radiation effects, the power control system shall power cycle the computer. So either autonomously or by the telecommand from the ground station. So the next subsystem is the structure and mechanical mechanism system. So let's take a look at the structure first. So satellite structure system as a main interface with the launch vehicle. In the case of CubeSats, the rails are the contact point between the satellite and the pod. So the outer dimensions, surface area and surface treatment of the rails and the outer envelope of the satellite, entire satellites are specified. So structure systems shall withstand the launch environment such as vibration, static, acceleration, shock, etc. So this picture shows the structure system of a 1U CubeSat as an example. So mechanical systems include separation switches, deployable antennas, deployable solar panels, shutters, booms, and any other mechanically moving structure elements on the satellite. So mechanical systems shall be safely stored during the launch to ensure the secure release of the CubeSat from the pod. So this picture shows a solar panel deployment mechanism as such an example. The next subsystem is the thermal control system. The thermal control of a satellite can be achieved in two different ways, so passive control and active control. So as active control needs electrical power, so heaters or coolers in general. So passive control is the usual thermal control concept of CubeSat. So passive thermal control utilizes different surface materials with different thermal optical characteristics in order to adjust the heat exchange among the satellite, deep space, and the Earth. So the next subsystem is the attitude control system. So attitude control capability is required depending on the mission operation of the satellite, such as pointing observation instruments toward the target, pointing high gain antenna toward the ground station for high-speed communication, or orienting the solar panels toward the sun for larger power generation. For attitude control, attitude determination is also necessary beforehand. So therefore, attitude determination sensors and attitude control actuators are required in general. So there are also two types of attitude control, passive control and active control. And there are many different kinds of attitude control modes, such as detampering control is one of them, which is for the after the separation from the launch vehicle or release from the ISS. And then pointing controls, such as inertial, area, target, velocity direction controls, etc. The last subsystem is the payload system. So payload systems are the onboard components dedicated to the satellite's missions. So good practice is to define the clear interface between the bus system. So in this slide, you can see the example of 3U CubeSat SQ. So this picture is showing the payload module of CubeSat. So 1U is assigned for the payload instruments, and 2U is assigned for the satellite bus system in this example. And finally, I will show you the harness cable of the CubeSat. So this is an example of 3U CubeSat SQ. I hope you can get the sense of how important and critical careful design of the harness system is, and that you assign enough envelope for them from the very beginning of the satellite development. And this concludes the explanation of satellite subsystems. Now we come to the next topic, CubeSat payload systems. So I go through the slides very quickly. So each CubeSat has its own missions. So the larger the CubeSat is, the more payload instruments can be carried, and the more advanced the missions are that can be conducted, as somebody asked questions just before. The example of CubeSat payload instruments include observation cameras, in situ space environment measurement sensors, meteor measurement sensors, communication instruments, engineering demonstrations, such as deployment mechanisms, advanced technologies, and so on. So today, I'd like to introduce you to 5 of these examples in the following slides very quickly. So first one, this is an example of Earth observation camera system. This is a 2U CubeSat RICO again. It was implemented with an Earth observation camera system, as well as a new sensor, star tracker, for the satellite attitude determination. So this is the first example. The next example is the meteor observation instrument. So this is a 3U CubeSat SQ again. So it was implemented with the meteor observation camera system. A gravity gradient boom was used to point the meteor observation camera toward the Earth's atmosphere for detecting incandescent meteors as they enter the atmosphere. So the next example is the signal measurement instrument. So recently, receiving and analyzing ground-based AIS signal, the automatic identification signal from space is attracting interest. So in this case, the receiver and the deployable directional antenna system are the payloads. So in this example, a 3-axis attitude control is utilized to point the antenna toward the Earth for detecting AIS signals sent from the ships, enabling tracking the position of the ships with higher geographical resolutions. The next example is the orbit demonstration of a thin film deployment mechanism. So this example is the 1U CubeSat Freedom deployed from the ISS, developed by Tohoku University. The payload was the deorbit sail for fast deorbiting and re-entry into Earth's atmosphere from the ISS orbit. So this CubeSat had actually no communication system or solar cells. So Freedom demonstrated on-orbit deployment of the same film based on the orbit sail, which can be utilized for space debris mitigation and prevention using atmospheric drag. Then the last example is the electrodynamic tether. So this is the 3U CubeSat ALEDT. So the payload is an electrodynamic tether for deorbiting and re-entry into Earth's atmosphere. So 3-axis attitude control is used to control the satellite attitude during the extension of the electrodynamic tether. The device will be useful for space debris mitigation and prevention in higher altitude orbit, as it can operate independent of atmospheric drag. So I hope you have a deeper understanding and clearer ideas now of what you can achieve by means of CubeSats. So now I'd like to conclude my presentation. Yes, so in summary, the characteristics of satellite technologies and CubeSat systems are described, and CubeSat standards are introduced. The functionalities of each satellite subsystem, including the payload system, are described in detail. So some example of CubeSat payload devices are provided together with real satellite projects. With this, I'd like to finish my lecture today. So thank you very much for your kind attention.
Okay, thank you very much, Dr. Kuwahara. I think that was a fantastic overview of CubeSat technologies, the different systems, and of course the subsystems. So now I'd like to move on to our next speaker, who is, Dr. Yuji Sakamoto. He's part of UNISEC, and he is associate professor at Hokkaido University. So yes, Dr. Sakamoto, you have the floor, and I see that you're sharing your screen right now.
Hi, thank you very much for the introduction. So, good afternoon, everybody. My name is Yuji Sakamoto. I am an associate professor from Hokkaido University, Japan. This is my information. So I made these satellites as a primary engineer or project manager. So I was working from 2006 at the Tokyo University, and now I'm working in Hokkaido University. So from my student today, I am dedicated to anyway for this micro and nano satellites through the design, assembly, validation. So I can say everything. So here is the outline of this lecture. Firstly, I'll explain the satellite operation and the orbit and the mission lifetime. So I think some topics are overlapping to the previous presentation, but I emphasize talk again. And then the fundamental items for satellite operations, they are communication system, ground station, link budget design, and things to consider in operational phase. So sorry, this content is wrong. So today virtual tour 1 and 2 are skipped. Okay, this is a real photo taken from the International Space Station. So 2 CubeSats are being released from the deployment to containers. So please consider what you need to think about for the operation of these satellites. So this is the repeat of again. The satellite rotates 14 to 16 per day in LEO, low Earth orbit. So the contact period is about 10 to 12 minutes, and about 4 passes are available per day. So please imagine the satellite will come from the horizon. It will pass over your ground station, and it will disappear into the horizon. This duration is just about 10 minutes. So in satellite operations, we send the commands to the satellite from the ground station and receive the telemetry data. So before the communication, we need to prepare the mission scenario and the detailed procedure of mission tasks. So our satellite cannot be repaired in orbit after the launch. So we can only communicate with them to conduct the planned missions, and sometimes we need to solve unexpected problems or troubles, anomalies. So variations of operation scenario and procedures need to be considered and tested before the completion of satellite development. Sorry, just a moment. This is strongly related to software concept and design. So I emphasize the operations are not the matter of only communication. So this is relating to the other subsystems, including command and data handling, attitude determination and control, and the power system, and thermal design, etc. Okay. So, sorry, this figure was already shown. The 4 micron nano satellite developers are low Earth orbit. This one or this one. is normally selected because there are many launch opportunities. And also a short distance to Earth has some merits. So communications transmitting power can be decreased, and high-resolution images can be obtained by a small telescope or camera. So a satellite released from the ISS have a 400-kilometer height and a 51-degree inclination from the equatorial plane. This is the merit for this orbit. The Arctic and the Antarctic area cannot be observed and communicated. So, and this includes the northern regions of Sweden and Norway. So their countries, from their countries, so the satellites cannot be seen. So you can communicate in this area. Also, the solar angle to orbit is changing every day, and this affects the daily observation timing to a specific location. So sometimes it comes only daytime, and sometimes it can concentrate at the nighttime. So it means that yes, we can communicate, but the satellite cannot see anything on the ground. So for ISS satellite, we need to consider a special heat environment. So the solar angle to the orbital plane, this is 0 degree. So this is better angle. It is changing from 0 to more than 70 degrees for ISS satellites. So the left figure shows the case of 0. In this case, the duration of the eclipse phase is maximum. So the generally ISS satellite orbit has a 90-minute period. So sunshine phase is 60 minutes and eclipse is 30 minutes. When this beta angle is increased, the eclipse duration is decreased to finally 0. So this results in an all sunshine phase. So it continues for a few days. So the temperature of all the components may converge to the maximum. Please imagine the temperature can be around 0 in cold case, but in the hot case, it can be increased to 40 or 50 degrees Celsius. So we must consider this phenomenon in thermal analysis and the power system design. So I recommend every mission should be suspended in this hot case to decrease the maximum temperature in internal components. And satellite lifetime deployed by the ISS is strongly related to atmospheric drag. So, in lower than 400-kilometer height orbit, atmospheric density is much higher compared to 500 or 600 kilometer. The height of CubeSat can be decreased by atmospheric drag because the drag force acts in a backward direction. So generally, 1U CubeSat can re-enter into the upper atmosphere with less than 1 year or half a year of orbital lifetime. So you need to finish your mission in very quickly. One example is 2-unit CubeSat, RICO. So this was deployed in 2012, and the weight is 2.7 kilograms. So this year, the atmospheric drag was stronger than normal. So because of heavier solar activity, the total lifetime was 10 months. And compared to the, this is another example. So in case of satellite Diwata 1, it is a 52 kilogram microsatellite, but it deployed from the ISS in 2016. And in the same solar activity condition, I can say the heavier weight satellite have a longer lifetime. So around 2016, the solar activity was weak. So the lifetime was finally extended to 47 months. So this was much longer than we expected before the launch. Okay, next chapter. In this section, I'll show the introduction to the communication system. A communication system is required for uploading commands from a ground station to a satellite, and for downloading housekeeping data and mission data, such as Earth image taken by satellite cameras. The first available frequencies are VHF around 144 MHz and UHF around 435 MHz. So they are in the range of amateur radio band, and the satellite must have missions for public amateur radio users or public students. And there is S-band 2 GHz and X-band 8 GHz. They can be also used for satellites, especially larger than 3U or 6U CubeSats, because of the possibility will consume more power. In both ground stations and satellites, there are receivers, computers, and transmitters. Firstly, the data in computer is decoded to a different format of bit stream and modulated to radio signals. They are transmitted from the ground antenna or the satellite. It is modulated in the receiver of satellite or ground station and decoded to original data in the onboard computer in satellite or ground computer. So general coding and the modulating methods are different in satellites. This photo shows the commercial products of satellite receiver and transmitters. This is the world's first CubeSat Site-4 and by the University of Tokyo. This has folding antennas that are deployed in space. This one. Lower frequency bands require longer antennas. So I will now introduce UHF and VHF signals. The merit in these signals is the reasonable prices for the setup of amateur radio ground stations. This make this frequency popular with many CubeSat developers. But the demerit is the slow data speed, such as 1.2 kbps or 9.6 kbps. So one reason is for this speed limit is the limited assigned bandwidth. Also, there are a lot of jamming noises, including illegal transmission signals on the ground. And these folded antennas must be automatically extended just after the deployment from the ISS or under rocket. So when the antennas are not opened, the satellite cannot receive any command signals or cannot send any telemetry data. And in most cases, any mission cannot be executed. So for S-band and X-band, we can use patch antennas. So that these frequencies are used for high-speed data communications. The example bitrate is 2 Mbps by S-band and 20 Mbps by X-band. And some satellite has more faster bitrate. Wideband wireless are available, especially for X-band. The demerit is a ground station cost, as it requires a large parabola tracking antenna system. The merit is that no deployable mechanism on the satellite side. So there is no low risk of command failure in the beginning of satellite operations. So the consumption of power can be higher than the amateur radio system, but I think this can be also tried even in the 1-unit CubeSat. When we cannot control the satellite altitude, omnidirectional antennas will be suitable, but the data rate will be slow because of low antenna gain. To increase the data speed rate, we will choose a high gain antenna, both in the ground station and satellite. A parabola dish will be used for ground stations, with a narrow beam patch antenna used for satellite. The performance of pointing accuracy is required for ground station to correctly track the fast-moving satellite. It is the same on the satellite side. The satellite must have the function of attitude control, and it should face towards the ground station direction during the communication. To decide the specs of the communication system, we need to understand the analysis method of link budgets. Acceptable data rates such as 10 kilobps, 100 kilobps, or megabps can be calculated by the balance of hardware specs. This technique is explained in a lot of reference books, and this is not a matter only for satellite design. So this is a very general knowledge for RF communications. So firstly, we need to decide the required hardware specs for both the satellite and the ground station. The data modulation type will change the acceptable noise levels, including FSK, BPSK, QPSK, etc. Communication distance is also important and will have a strong impact on deciding the data rate. So this distance is maximum when the satellite is around the horizon, and minimum when the satellite is in maximum elevation. And also by the atmospheric drag, so that this distance can be decreased gradually. Okay, next one is ground station. So in this section, I'll talk about the ground station related components. So the left figure shows a Yagi antenna for amateur radio communication. And the right figure shows the dish antenna for S-band or X-band communications. These antennas are controlled to the direction to satellite position during a 10-minute observation window. So they are being moved to follow the estimated direction. So future satellite position direction can be calculated by the two-line element. We call it the TLE. So TLE data is distributed by a public website, celestrak.com or etc. All the space objects are being monitored automatically, and their orbits are open to public. So I think the a bit negotiation is necessary, but you can get the data just after the release to space. This figure shows the satellite position and the ground station location. The circle of this is a satellite. The circle of the satellite indicates the visible area from the satellite. Only this circle. The ground station must be included in the circle of communication. The best way is to prepare ground stations around the world to increase the amount of mission data. So amateur radio satellites, every country can be accepted for the communication. But for remote sensing or other experimental services, they are only allowed to communicate with specific countries. It's defined in ITU applications. Okay, operation software is also important to establish an automatic system. You will be very exhausted if you don't have an automatic system, especially for ground station. This antenna control, the right side, the antenna control software is developed by university, the Tokyo University, including automatic control of the manufacturer software. So after the completion of automation, so we don't need to care about the antenna control. So operators, satellite operators, can concentrate on the data communication with satellites during the observation distance. So we don't need to care about the satellite tracking. So telemetry data is distributed from the receiver, but it is very bare and raw data at first. So we need to convert them to the satellite status or image data by individual conversion manners. So this kind of satellite operation software will be prepared for each satellite. Okay, so this section topic is satellite launch and first contact. So I talk about the case when we use the service of ISS Kibo, satellite deployment service. The satellite should be delivered to JAXA several months before the launch. So the CubeSats are assembled into the JSSOD. It is a frame in the left figure. So this is deployable container for multiple CubeSats. So these days, the variation of containers are being increased. So the latest information must be checked to JAXA. After the handover ceremony, so checkout and ceremony, JSSOD, including CubeSats, it is shipped to the launch site for further integration to the cargo spacecraft. So the cargo spacecraft had several variations. So the one example is HTB is launched by rocket H2B from Tanegashima Space Center. So the cargo spacecraft, the Cygnus, is also the popular available. This is launched from the United States. So the CubeSat is handover at Japan, and it is shipped to the United States. HTV approaches and docks to the ISS after a few days. JSSOD containing CubeSats are handled inside the ISS. CubeSats experience mechanical vibration during this launch. So the power supply must be turned off at all times until deployment to space. So CubeSats are prepared for deployment by astronauts. So JSSOD and the deployment to pallet are transferred to outside. So I think you can see a CubeSat inside of JSSOD. So they are attached to the tip of the robotic arm on Kibo. Then the astronaut triggers the switch for the deployment. This is a memorial photo when the Filipino microsatellite, Diwata-1, was released from the ISS in 2016. So this is not CubeSat, it is 50 centimeter class microsatellite. After the deployment ceremony, we need to come back to the ground station to catch the first signals. So most CubeSats automatically start their functions in space, including RF transmission. So we observe the first signals from satellites at ground stations. I think this is the most exciting moment. Satellite health is checking, including normal power generation, normal battery charge state, and the moderate temperature of components, etc. This is a release event of the 2-unit CubeSat Raiko just after deployment into space. Raiko started to take a lot of photos without altitude control. In those photos, the ISS was included, and Earth direction was also captured. After the first telemetry monitor, we need to confirm the successful command uplink. A lot of CubeSats have defects in the command function, unfortunately. So careful of the electrical noise environment inside of the satellite. Even if you think the link margin is enough, but finally, if there is strong noise inside the satellite, the receiver cannot find a weak signal from the ground station. Okay. In this section, I'll talk about mission operations. So this is appearance of our daily operations. We use the satellite control software, this one, and upload the prepared commands. Then monitor the status and download the image data. In this example operation, we check the result of altitude control pointing to Earth direction. So it is quickly download the thumbnail image data. When everything works well, we can obtain the desired mission image data. So this was captured by a very wide fisheye lens camera. So the Earth direction is captured like this circle. So there is a Japan Islands like this. So this is the function of satellite control software. In most satellite operations, you will make an original software for status decoding and quick command operations. So this status window is showing solar power generation, including voltage, current, and power, and power consumption by bus components, and the battery charge and discharge state, and the temperature, and on-off state of each bus component. Sorry, this one. And also it has the quick command buttons on and off. So red alert lamp. So now everything show green state, but the red alert lamps are important for us to notice emergency conditions immediately. Command counters. There is a command counter exists. So command counter is incremented by single command reception. So it will be very convenient because the command link is not stable anytime. Okay, I think that's I should finish, but okay, I'll quickly explain. I don't recommend using only real-time commands. So I introduce a stored command function. So this is important when we want to execute tasks in visible time. So uploaded commands are not executed instantly, but just stored in the onboard memory. So each command line includes a specific date. This is a specific date and waiting time. So I recommend a combination of specific data and waiting time. So this is convenient for reusability of the procedure. This is the example of camera on, attitude control to target, and take a photo, and the camera off. Okay. So by changing the date of the first line, we can reuse this procedure again in future tasks. So this text file is converted to the hex binaries, including header codes and the checksum codes, and this is uploaded to the satellite. Okay, I'll skip a bit. Okay, if we want to increase the precision of attitude control, we need to survey flight data and compare them with simulation results. Then update their parameters, such as sensor alignment. So I want to emphasize, we often mistake the definition of plus and minus direction, minus signs. And these kinds of mistakes cannot be excluded, sorry. So you must prepare the update function for every parameters. Okay, this is the image of an operation routine. Firstly, we will make the operation plan. This is a kind of text file I explained. So we will create a new procedure or just assemble the previous procedures by adjusting the first line specific date. So we need to analyze the orbit and estimate the suitable timing of future tasks. I think this work will consume an enormous amount of time, and the mission planner will be very exhausted. After finishing command preparation, the upload task will finish in 15 minutes or 20 minutes. So after the completion of the upload, in the same parse or following parse, the ground station will receive telemetry data, including mission images. So this can be manned or unmanned operation. So by preparing the automatic receiving system, operators can sleep very well at night or weekends. Okay, I conclude my presentation. So I want to emphasize again that anyway, the important thing is the link budget design is important, but the noise condition inside of the satellite must be carefully surveyed. So in the development test phase to avoid the critical mistakes or failure. Okay, I'll finish my talk. Thank you very much.
Thank you, Dr. Sakamoto, for this really intensive presentation. And I see a lot of questions coming in, so I'd like to dive into all of that. Of course, I'll take half from the room and half online. So I will give you a few minutes for the people on site to think of your questions while I start addressing some of the ones that are coming in here. So the first question, let's see, sorry, there's a lot of questions coming in. Sorry, give me a second. So maybe this is to Dr. Kuwahara, or maybe it is to Dr. Sakamoto, any of which, if any of you can answer this. What are the technical challenges for components to be suitable and sent to space? So what are the special characteristics that you would need to consider when you send something to space, especially regarding electronic components?
I think I go first. Thank you very much for the question. I think you, Hazuki-san, picked up a question from the online, right?
Yes, online.
Okay,
yes.
okay, I could see that. So first of all, the component should withstand, as I said, the launch environment and also the space environment. So for example, radiation. So terrestrial use components need to be tested for the space use from that kind of point of view, or you can use space qualified components, but space qualified components are of course very expensive. So one good way to develop very cost effective efficient CubeSat, you use terrestrial use components and test it against the space environment. So radiation is one of them. And thermal is also one important topic. Structure, shock, all these are kind of specified in the engineering documents. So I recommend you to refer those engineering documents about CubeSats. Thank you for the questions.
Thank you very much. Dr. Sakamoto, do you have anything to add to that? You're muted.
Okay, my idea is anyway, we need to test the vibration, the thermal and the vacuum. I think the most of electrical components will not have trouble in just a vacuum environment. So, but I think there are weak components for temperature, especially the very cold temperature. So I think that there is the recommended temperature range is it has some grace, and the general ICs can survive, can work normally only in 0 to 40 or something, and I think the industrial grade will have the -40 to +80 degrees Celsius. So we need to screen if we want to use the very general, the public commercial product. And is for vibration, we typically treatment to put the silicone coating or something on the PCB board. So without any treatment, we can encounter the trouble in the vibration test. So some ICs are they're broken in the hard vibration. I think that most of components can survive, but I can say that any one mistake will the satellite function can end in failure. Only one mistake, so we need to be carefully check the risks in the commercial boards.
Okay, thank you very much. I'd like to address one more question from the online, which is how is the lifetime of a satellite calculated?
中本先生がよろしそうですね。いかがでしょうか。
Dr. Sakamoto? How is the lifetime of a satellite calculated?
Satellite
Lifetime.
lifetime. Calculated, so okay, estimate. I think it's a good question. So actually, it is very difficult. So yes, by assuming the very typical atmospheric drag, we can estimate it, but it can be very hardly changing. So generally, we assume the 11-year cycle of the solar activity, but I think it is not stable in these 10 years. So I think it's very difficult to estimate. So I have no good answer for this.
Dr. Kuwahara, do you have anything to add?
Yes, so we can calculate the theoretical motion of the spacecraft due to the orbital dynamics. And we also pay attention to the atmospheric drag and those kind of environmental effects. With that, we can kind of numerically estimate the future orbits of cubes of satellites. I think this was the kind of what was asked, I think, from the audience.
Thank you very much.
Thank you.
And sorry, one more question from online, and then we will move to on-site. So how do you analyze the data coming from the satellite? I will repeat, how do you analyze the data coming from the satellite?
Sakamoto Sensei.
Yes, I understand the question, but it's very the general question. So analyze. Yes, I think the comparison to the simulation data will be important, especially I think the attitude determination control system is the main task for the analysis of telemetry data. So we need to prepare the attitude simulation environment. So before the completion of satellite. So anyway, in advance, it is prepared and the test the attitude controller program is suitable for space environment or not. It can work well or not. We need to estimate. Then after we get the data, we will find any errors or the mistakes or something. So it can be found by the comparison with the simulation data.
Okay,
Well,
Dr. Kuwahara, anything to add?
Nothing special. Thank you. Yeah.
Okay, now I'd like to ask some questions to the people here in Tunisia. So does anyone have any questions? Okay. And to everyone, I will repeat the question.
I have two questions actually, if you don't mind. So my first question is, we say that the larger the CubeSat is, the more difficult mission it can do. So can we imagine that the satellites will be able to take place the bigger satellites such as Tunisia 1 to have the location more precisely? My second question is, in the communication between satellites, what type of attenuation and losses to be considered? Thank you.
I don't know if the professors heard, so I will try to summarize the question. The first question was about bigger CubeSat. And sorry, can you rephrase your question again?
Take place other bigger satellites as the geostationary satellites to have the location more precisely.
Do you mean that can a CubeSat be on a geostationary orbit, or because satellites? Of course, you can start with the CubeSat, but you can keep developing more satellites. So it depends on what your mission is, what you want to accomplish. So it depends on you how big the satellite is actually, and which orbit you want to put on. Does that answer your question?
Yes.
Okay, and the second question?
The second is what type of attenuation and loss will be considered in communication between two satellites?
Between two satellites?
Yes,
on
in the space.
So I don't know if the professors heard, she is asking about what we need to consider when we communicate between two satellites on orbit. Am I correct? Yes.
OK。僕が行きましょうか、坂本先生。
はい。
はい。So, inter-satellite communication. So, simply, the link margin should be enough between the for the communication, either independent of whether it's radio frequency or it's by the laser communication. You need to have enough power for the communication so that the receiving satellite can receive the signal and then detect the information hidden in the signal. So from that point of view, you need to have a strong enough transmitter and also big enough antenna and sensitive enough receivers and so on. Did I answer to your question?
So there is no losses. It is considered as a perfect link with no losses.
I think there is no perfect link. There's always something that you need to consider within the satellite communication. So I don't think there's anything such as perfect in space, but it's the best thing you can do. Okay, thank you. Is there another question? I saw that girl, her, the one standing,
Thank you for this presentation. So my question is, are there any specific solar cells dedicated to space? Because I noticed in the first presentation in slide number 20, I'm not mistaken, that the solar cell efficiency is higher than 29.9 or 5 near to 30%. While as far as I know that solar cells that use on Earth, solar cell efficiency doesn't exceed 17 or 19%. Thank you.
Cynthia, were you able to hear the question? It's about solar cells. It was about your presentation. Can you
Solar cell efficiency?
solar cells efficiency?
Yes, it is mentioned in the first one that it is higher than 29%. While what we use on Earth the solar cell efficiency don't exceed 17 or 19%. So I find that this number is very high when it comes to solar cells. So are there specific solar cells dedicated to space missions, or they are the same for both and it differs between Earth uses or space missions?
So to summarize, are solar cells used for space missions different from on Earth application? Is there something special about solar cells on the satellite compared to normal stuff on Earth?
OK, so if I understood correctly, you're talking about the efficiency of the solar panels or solar cells, right? So they are different from normal solar cells. So for space use solar cells, I think you were talking about page 20, I guess, if you have access to the internet. So for the space use solar cells, solar panels, the efficiency is now about more or less up to 30%. And then they are very expensive. They are very expensive. So multi-junction solar cells, multi-layer solar cells, they have a very high efficiency, higher efficiency than the normal commercial terrestrial solar cells. Thank you.
Thank you.
Okay, just one more question from the floor, okay?
Thank you so much for thank you for your valuable information. And my question is, what is the minimum number of geostationary satellites that will allow for worldwide communication? And I have a second question, which is, what is the maximum number of satellites that we can put through orbit?
Okay, I don't know if you heard, the first question was, what is the minimum amount of satellites that you would need on geo for communication?
Yeah, to allow the worldwide communication.
Okay.
My first question is, what is the minimum number of geostationary satellites that will allow for worldwide communication?
Sorry, very difficult to kind of dictate. So your question is how many satellites we need on the geostationary orbit to, could you repeat it?
To have worldwide connection.
Worldwide connection. Okay. So theoretically, maybe 3 big satellite, maybe more than 3. But in practice, there are lots of communication, large communication satellites. So I don't have clear answer to your question.
Okay, and he said 3, but then, yeah, it depends. And the second question?
Yeah, my second question was, do we have like a maximum number of satellites per orbit? Or we can put like,
the question is the maximum number of satellites on orbit. So there's GEO, LEO, there's different satellites, and how many satellites can we put in one orbit?
In one orbit?
Yes. So
In
for
one.
let's say GEO, how many satellites can we put up?
Okay, so
Theoretically.
thank you. So limitless, I think. There is no limit, I think. So in principle, the space environment is kind of three-dimensional. So the maximum number of satellites you can put on a single orbit is depending on, for example, the radius of the orbit. So if it's bigger, you have more space. And if it's smaller, you have less space. And then if you tilt your orbit, and if you have multiple orbits, you can put many more satellites. So this kind of idea is, kind of discussed as space traffic management. So in the past, there is no kind of active, regulations about the satellite space traffic management. But nowadays, many, tens of thousands of relatively small spacecraft are launched into orbit, and we need to start seriously, thinking about space traffic management. So your question is, I think, related with that kind of, let's say, issue. Thank you.
Okay, thank you very much. One last question that two more questions that I want to take. I thought one is interesting, so I want to pick it up. Why is the focus on CubeSat nowadays? And there's smaller satellites such as femto satellites. So why are we talking so much about CubeSat these days? I believe you answered it in the chat, Dr. Kuwahara, but can you also answer it to the people here in Tunisia? Why are we talking so much about CubeSat when there's smaller ones and of course there's bigger ones? So
okay, so yes, thank you. I think I have answered like online by text. So it is recommended in general that all the space objects can be observed from the ground to make a catalog of space object and also kind of track the position, orbit of each spacecraft. So they need to be bigger than certain, size. So the one CubeSat is kind of more or less that size. So therefore, the FEM satellite or maybe even smaller satellite can be theoretically developed, but they cannot be observed from the ground. So it is not recommended to distribute such a small spacecraft from the debris mitigation point of view. So if the observation capability of ground makes more, advancement, then maybe we can utilize even smaller spacecraft in the future, but we don't know how it goes. Thank you.
Okay, thank you very much for answering the question. We're running out of time. So there's just one last question that I want to address is, how can I enlarge my knowledge about this field? As I explained in the beginning, please go to the UNOOSA Access to Space for All website. We have many opportunities that can help you access to space and learn more with the different educational webinars, with the workshops, and everything we have. And regarding the questions that we were not able to answer, we have a wonderful series of KiboCUBE Academy webinars that cover all the different aspects of satellite development, operation, and utilization. So I believe a lot of the questions may be answered if you have a look at all these webinars. So to everyone, I really recommend you to go over this whole satellite webinar series. Okay, so with this, I'd like to, because we're running out of time, close the Q&A and bring in our closing remarks from JAXA. So from Dr.
Thank you. I'm Izumi Yoshizaki. I'm a project manager for the CubeSat program at JAXA. Thank you very much for joining us at this KiboCUBE Academy. I think you learned well about how, what a CubeSat is, how to design it, how to operate it. And I think this CubeSat is very small, but to develop and operate it requires high-level knowledge. So by doing this challenge, we can go to, it'll be a very good one step, the first step to develop a real large satellite. So we also introduced about the KiboCUBE program, which is supported by UNOOSA and JAXA. And the professors in UNISEC are very happy to answer your questions anytime. So we are looking forward to collaborate with you in the near future.
Thank you very much, Dr. Yoshizaki. And with this, I'd like to close our first on-site and hybrid on-site online KiboCUBE Academy. So as I've explained earlier, all the presentations and the recordings later on will be available on our website. So please make sure to check that out and share it with your colleagues and friends who are able to come here. So with this, yeah, thank you very much. And we hope to have another KiboCUBE Academy soon. Thank you very much. Have a nice day, everyone.